Hi, I am Ismi and I will be presenting my work Privacy in Urban Sensing with Instrumented Fleet using Air Pollution Monitoring as a use case. To introduce the problem of privacy in urban sensing, consider scalable sensing of particulate matter. Here, to measure air pollution, cabs of transport partners are fitted with PM sensor which measure air pollution, GPS sensors to tag data with location information. Here, cabs measure air pollution as they roam around the city. The sense data is then sent to a private server of the transport partners. Now, when a client queries the server for PM uh, value, the server responds with the corresponding value. But what about now, when there is no information, or because there was no cap at that particular location, the server has to reply with no value. This will give rise to utility problem for client as well as the privacy problem for server. That is, the legitimate clients like commuters or environmentalists wants the server to respond to each and every query, while server does not want to reveal the location of its cabs and fleet size. This gives rise to the underlying threat model, where cab company acts as a data provider and wants to know about the query location of commuters, environmentalists revealing about their behavior, their nature, whereas rival company acting as data consumer wants to know about the business model of transport partners, that is, where are no cabs or where the demand for cabs are high to basically divert their cabs to the location at such places where there are no cabs. To preserve the privacy in such scenario, we release the data securely by balancing privacy, latency, accuracy trade-off. Recall, when there is no cap at a particular location, the response server gives out is no value. We can avoid it by using interpolation technique such as Gaussian process regression, where each grid cell introit gives a tuple value, that is the interpolated pollution value and the confidence in the interpolated value. Here the interpolated value is represented by a posterior mean mu p, and the confidence in the interpolated value is given by posterior variance sigma square p. We have also have to look out at the computational cost of doing the interpolation. So for server, it is simply doing the GPR inferencing and training, while for client, it is to compute the query locally at its device. But what about the privacy? As we see that client does not send its query location to the server, it gets complete privacy. However, from the plots, we can see that the cap location can be discerned by the posterior variance, represented by the blue color. Posterior mean does not show direct correlation with the cap location, and hence we cannot see the exact cap locations in the posterior mean plot. Here we have complete privacy to clients and limited privacy to servers. To prevent leakage from posterior variance plot, we apply differential privacy. Existing solutions apply differential privacy on posterior mean, but not on GPR variance. However, we need to apply DP on GPR variance and it leaks the trajectory information. We use Laplace mechanism to provide differential guarantees to our variance function. For that, we need to compute sensitivity and choose an optimal privacy budget. After applying DP, we can release differentially private maps. However, as DP introduced noise in the system, we have to consider the accuracy. Computational requirement of applying DP, as we have noticed, is negligible in comparison to applying Gaussian process regression. We varied epsilon, that is the privacy budget to achieve different privacy accuracy settings. We see that when epsilon is 10, we can still make out the location information as can be seen from the middle graph. However, reducing epsilon degrades the accuracy as we can see from the right hand most graph where the epsilon value is 0.1. So as we are introducing more and more noise into the system, the accuracy degrades, but we get higher privacy. As we have to add Laplacian noise to each and every grid cell points, the noise introduced in the system is quite high. This motivates us to use secure two-party computation, where two-party computes function on their private input. This computation only reveals the output of the function, and all the intermediate computation and the input remains private for both the. Secure 2PC give us our final end-to-end secure query response system. Here client does not get full privacy, instead it generates private query location vector V. This vector hides the location in which the client is interested. Client then communicates with server in an oblivious setting to get the query response. For each query, server set a threshold on the size of client input vector to prevent leakage from a length 1 query. It also applied differential privacy in a secure circuit to protect against smartly crafted queries. We will discuss it more in the next few slides. We see that 2PC is compute heavy, so we need to examine the cost of communication and the computation for our query response system for different supported. Next, I will discuss how query response system works. As we discussed earlier, a city is divided into grid cells. Client is interested in some location within yellow rectangles. So it generates a obfuscation rectangle and send its coordinate to server. If it needs more privacy, then the size of obfuscation rectangle will be large. Based on the query input, server computes the output securely. Consider this yellow region as a grid with cells numbered from 0 to 8, and 4 and 5 cells are the location in which the client is actually interested. He then maps the cell information as a vector V, where 1 corresponds to 4 and 5 location. He then need to create a thresholding circuit such that the query reveals a valid answer only if the number of grid cells within the obfuscation rectangle having one value is greater than the set threshold alpha. Companies can set this alpha value high so that they have high protection. Based on the output, set selection circuit selects mu and sigma square value only where the V value has 1. After that, the query function and propagation function uh, is computed based on the query type. However, this might release the location information if the queries are crafted smartly. For example, query 1 and query 2 have an overlapping region, which can also be seen when we generate the location vector. This might leak posterior variance. To avoid this, we add additional sub-circuit in the previous example for TP generation, TP noise addition. What happens after getting the output of query function and error propagation, we add Laplacian noise in the output posterior variance to avoid leakage in the previous example. We have considered multiple queries in our system like average, minimum, count, range. To compute query function on pollution value, it is very straightforward. But what about the posterior variance sigma square p? So we have used the error propagation methodology to compute variance per query as given in the formula in the slide. The thing which we have to consider is that error propagation can only be applied on differentiable functions. For each query type, we find the optimal differentiable function to represent query, and then we differentiate it to get an error propagation function such that we can represent it in a circuit. So here are the details of implementation of our system. We have explored multiple techniques and different data sets to evaluate our system. For our first public pollution maps, we have used Gaussian process regression and evaluated the system using Delhi dataset and Beijing dataset. Delhi dataset is basically we have collected it by ourselves by fitting pollution sensors on 10 different buses which moves around the Delhi city. This data set is relatively smaller in size, so we have used another synthetic data set which we have generated by using mobile taxi data set of Beijing publicly available and the static data from pollution monitoring stations of Beijing. This gives us a mobile pollution monitoring data set. In the second case of differentially private maps, we have used Gaussian process regression along with differential privacy. For this, we have used one more dataset, that is OpenSense dataset, which is collected by fitting the pollution sensors on trams in Zurich. That is also a publicly available open dataset. For our final system, we have used a combination of Gaussian process regression along with garbled circuit and differential privacy. So since we cannot use Beijing dataset as it does not have the start and end trip information of a taxi trip, we used Porto taxi dataset, which has a number of taxi trips with start and end locations information. For differential privacy evaluation, in this case we have again used the OpenSense and Delhi datasets. To the server configuration and the client configuration of our query response system are as follows. For a client, we have used two types of client. One is a PC client and another was Android client. For the implementation of garbled circuit, we have used the EMP toolkit library. And for Gaussian process regression implementation, we have used the GPI library. We evaluated our query response system on photo taxi dataset. We can see from the graph that 80% of the trips are less than 15 kilometers, which corresponds to query location length of 100 in the dataset. We considered the following performance metrics like latency and bandwidth. We see that the fastest query is average query with a response time of few seconds for mobile user and giving out response to laptop users within sub-seconds. As average query is computationally less complex than minimum range, so the response time for average query is much smaller than the minimum and range query. We also evaluated the CPU usage and the energy of doing queries for range, and we see that if the query size is 100, then the average CPU utilization is below 10%, which accounts to 0.24% of the total device power. So to conclude our work, we presented a privacy versus utility trade-off study for fleet company and sensor data clients. We first used GPR to hide locations without vehicle information, but we see that the GPU output still leak out fleet information. We then used 2PC to answer queries with GPR output at low latency and bandwidth for mobile clients, preserving client privacy, fleet privacy. We additionally used differential privacy on the 2PC results to protect against smartly crafted 2PC queries. We also motivated the use of two-party computation, showing that applying differential privacy after GPR cannot balance the privacy utility trade-off in every data set, as we have to add noise to each and every grid cell points. We also show pollution aware Android route apps, which highlights how scalable data sharing can aid citizens to make more informed choices in reducing personal pollution exposure. Thank you. I will be happy to take questions now.